Now we said with intensity that the waves spread out all directions, that we are dealing with what we call an omnidirectional source, and therefore, since it's omnidirectional, the waves go in all directions. So pretty much anything that makes any kind of noise or makes any kind of light goes in all directions. Now we can do things to kind of direct that in one direction or the other with reflectors, but generally these things go in all directions, that somebody can hear you speaking even if they're behind you. Certainly the intensity is bigger if they're in front of you, and there are some effects like that, and we're not going to worry about those. So we're just going to say for any emitter, the sound goes out in a spherical direction, meaning all directions, and therefore the area that we're going to use is the area of a sphere. So that means that these wave fronts are concentric arcs, and the distance between each front is, we're going to say that each one of these lines represents a crest, and each one of these then is one wavelength apart, and so the distance between these is a lambda, or the wavelength of our light. And then these lines that go perpendicular to the wavefronts are called rays. And those as rays of sunshine. You can also have rays of sound. So these are the lines pointing perpendicular from the source out. And a plane wave is something that's very far away from the source, so the rays are almost parallel to each other. And this is what we see for sunlight on the Earth, that the sunlight comes down pretty much parallel. And so we don't get weird effects of angles that you do for lights on the interior, where you can see the light rays coming out at angles. So they're almost parallel to each other. And that means this wavefront are pretty much straight lines perpendicular to those rays. So this means that if we use this inverse squared, and we say how does the power vary as we go away from a source, then if we write the ratio of the intensities here, and then we say the power is equal to, the intensity is equal to power over our area, so we write the areas here, we end up with a relationship on how the intensity varies with the distance. So as we go farther out from a source of light or a source of sound, the amplitude of those waves gets smaller, because not that the source has less power, it's just that that power has to be distributed over a greater area. So the intensity goes down. So the loudness goes down, the brightness goes down. The brightness of the sun at Pluto is much less than it is on the Earth, just as the intensity of the sound far away from a rock concert is much less than it is close by the speaker. So here we're going to be, here we have a jet engine, so something that's really loud, and we're at 30 meters. We measure it to be 130 decibels. So we know this is basically R1, and this is our sound level 1, so I call that dB1. And we want to figure out how far we have to go to make it basically not hurt. So this is my dB2. And again, we can't really do anything with the decibel numbers. We need to convert those to intensity using the intensity formula. Is equal to I naught times 10 to the beta over 10. And so I naught is again 1 times 10 to the negative 12 watts per meter squared times 10 to the 120, or 130 over 10 gives me 10 watts per meter squared. And then if we do the same thing for 110, dB gives me 0.1 watts per meter squared. So now I can do some math. So I1 over I2 is equal to R2 squared over R1 squared. And so R2 squared is equal to I1 over I2 times R1 squared. And so I1 was again 10 watts per meter squared over 0.1 watts per meter squared times my original radius of 30 meters squared gives me 90,000 meters squared as R2 squared. So So R2 is equal to the square root of 90,000 meters squared, or 300 meters. So to go far enough away to make the jet engine not hurt your ears, you have to be at 300 meters. So here are those values again, nicely written out. And that is the end of this section.